starting out, factoring polynomials. We factored before in the past. We factored things like x squared minus 5x plus 6. We factored quadratic trinomials. But again, this is quadratic. Today, we're factoring cubic, quintic, quartic, higher order polynomials. But just a reminder, because you will need this today, to factor a quadratic trinomial, we ask ourselves, middle term, what adds to give me that -5, what multiplies to give this positive 6, which in this case would be, what's your numbers? Good, -2 and -4. Multiplies to give you positive 6, adds to give you -5. That's factoring quadratic trinomial. But today we're factoring higher order stuff. Starting with a cubic equation. First it says determine whether x plus 4 is a factor. We're going to start out taking baby steps. They're going to give us something, and we're going to decide, is this actually a factor? And if it is a factor, we're going to factor out what we're left with the rest of the way. Reminder about what a factor is. You've got the number 8. Is 4 a factor of 8? Question mark. What do you think? What is a factor? Is 4 a factor? Yeah, there's a 4 in there, right? How can we assure ourselves that 4 is a factor? Divide it into 4. But not only because I can divide 5 into 13. But what's different about it if it is a factor? It has a no remainder. 4 is a factor of 8 because if I divide 4 into 8, I get 2. Which means I can break down 8 into 4 times something. When you're factoring, the process of factoring is it's breaking something down into its factors, breaking something down into multiplication. And keep that in mind as we're working this problem. We want to know, is x plus 4 a factor of this x thirds minus 13x plus 12? To determine if it is, we divide. And we're going to use synthetic division to do this. To divide by x plus 4, we put -4 in the box. We're dividing it into 1x to the third. Notice there's no x squareds. I'm colored today. Minus 13x's and a positive 12. According to synthetic division, bring down the first number and multiply. Add the 2 together, multiply. Add the 2 together, multiply. Add the 2 together, the last number is 0. That last number is your remainder. So is x plus 4 a factor? Yes. Now here's what I want you to get used to. The same way that since 4 was a factor of 8, we could break 8 into 4 times 2. What you just did is you took x to the third minus 13x plus 12, and you divided it by x plus 4, and you got this stuff. Which, by the way, this stuff is 3, -4x, and positive x squared. So what we're going to do is we're going to take and we're going to rewrite this. We're going to rewrite x to the third minus 13x plus 12 as, somebody turn that back into a polynomial, x plus 4 times, what did I say this was? X squared minus 4x plus 4. So we factored it. That's our first step of factoring. We took our x to the third equation, we broke it down to x stuff times x squared stuff. Now let's go a step further. We know how to factor this. That's what we just did. X plus 4 times, and clean that up now. X adds to give you adds to give you -4, multiplies to give you 3. Jackson, what are those two numbers? So now that x to the third stuff is factored complete. Next step, notice on that last problem, was it x minus 4, or x plus 4 was a factor. Well, how can we determine what things might be factors? What are some possible factors of a certain? Because on that last one they gave us, they said, is this a factor? Will it factor into this? How can we determine if something is a factor? We have what's called the rational roots theorem. The rational roots theorem is, it gives you a list of all the possible things that something can factor into. And notice it's a rational roots theorem. I need to explain the relationship between factors and roots before we go any further. X plus 4 on that last problem was a factor. Think about about if you were solving the equation though? Or let's do this. Y equals x minus 3 times x plus 2. X minus 3 and x plus 2 are factors. Something's been factored here. It's been broken down into its factors. Now, let's talk about the relationship between that and a root. If you graph this, hopefully we all know that if we graph this, we're going to get a parabola. What's going to be the x-intercept of that parabola? How do we find x-intercept? Do you remember? Put a what here? 0. Put a 0 in for your y. We solve it. What are my two x-intercepts? 3 and negative 2. My graph is going to cross, and it's going to look something like this. My graph is going to cross at negative 2, and my graph is going to cross at 3. Negative 2 and 3 are roots. X-intercepts, zeros. There's 3 different names for it. So if x plus 4 is a factor, you see the relationship. X minus 3 is a factor, 3 is a root. X plus 2 is a factor, negative 2 is a root. X plus 4 was a factor, negative 4 was a root. A root is the same thing as an x-intercept. An x-intercept can also be called a 0. There's three different words you use interchangeably there. Make sure that if you see those words, you know that it's the same thing. So go back to synthetic division. If you're dividing by x plus 4, x plus 4 is the factor that you're dividing by. Now we got some new terminology. If you're dividing by x plus 4, what do you put in the box? The root. The root of that value. Because a lot of people have issues. What if you're wanting to divide by something like 2x minus 1? What do you put in the box? The root of that. Set it equal to 0, you put 1/2 in the box. So if you're dividing by x plus 4, negative 4 was the root of it. Okay, here we go. Find all the possible rational zeros. And already, they're using, instead of roots, they're using the word zeros. All the possible rational zeros for each polynomial function. Here's what the rational root theorem says. The rational root theorem. It says you can find all the possible rational roots by taking the last number and taking the first number. If it's got to be in descending order. Notice x to the third down to like it normally is. Take all the factors of the last number over all the factors of the first number. And I'll show you what we're going to do with it. The factors of 8 is 1, positive, negative, negative 2, positive, negative 4, and positive and negative 8. That's just a list of all the factors of 8. Over all the factors of 3, which is simply positive, negative 1, or positive, negative 3. The combination of all of those factors are all of your possible rational zeros, the possible rational roots. Let's start with 1 over 1. 1 over 1 is 1. We're going through all the possible combinations of these. 1 over 1, now let's go to 2 over 1. We'll put commas. 4 over 1. And 8 over 1. That's 8. Go through it, start over again. We've used all these. 1 over 3. 1 over, or excuse me, done with that one. 2 over 3. Positive and negative. 4 over 3. And finally, 8 over 3. That is all your possible rational roots. So my question is, and when I say possible rational roots, we all know what a root is now. A root is where this thing's going to cross the x-axis. That's a root. So how do you know which ones are the roots? We need to go back to the synthetic division. They gave you one, and they said, is this one? Is x plus 4 a factor? Is negative 4 a root? They gave you one to try. You have, on this problem, 1, 2, 3, 4, 5, 6, 7, 8, 16 to try. The positive and negative versions of all those. How do you know which ones work? try them to find one that works. You're going to get really good over the next couple of problems at doing synthetic division. But because for now, that's what we're going to do. We're going to test them. We're going to see which one works. They're not good. Finding all the zeros. Let's work one that way. We're gonna take one problem. We're gonna work it that way, and then we're gonna talk about an easy one. But I need you to know how to find all the possible rational roots. I need you to be able to go through that process. On this one, find all the real and imaginary zeros for each polynomial function. So step one, I need to know it's x to the third. I can't factor just x to the third like I do quadratics. So I need to know what's something that might work. The way that we find that is by finding all our possible rational roots. The possible rational roots are all the factors of 6. You're going to find out that there are certain numbers that you really don't want to see, like 12. 12 is not a fun number. It has lots of factors. 24 is not fun. 32 maybe. Yeah, this number is a bad number. Over all the factors of 2. So here's all of our possible rational roots. 1 over 1 is 1. 2 over 1 is 2. 3 over 1 is 6 over 1. It's 3 and 6. 2 over 1, or excuse me, 1 over 2 is a half. 2 over 2. You had to put 2 over 2? Already listed. 2 over 2 is 1. 3 over 2 and 6 over 2. You don't have to put 6 over 2, it's already listed. There's all your possible rational roots. So here we go. Now that we have all of our possible rational roots, let's clear this out and bring it around. You start working. You start picking. Okay, now again, keep in mind, these are roots. So when you're doing synthetic division, what are you putting in the box? Those. Because these are not your factors, these are your roots. What if 2 works? Let's try that. What if 2 works? Then what was a factor? X minus 2. Y'all see the relationship? So let's try 2. Why am I trying 2? I don't know. For lack of a better place to start. Question. 2, 4, 1, 2, negative 9, negative 18, negative 12. Did it work? No. That's what you do. Pick a difference. You're fixing to find out how lucky you are. Some of you will pick 1 and for some reason, wow, it seems like the first one I picked always works. Some of you will pick 9 and 10 and 11 and get very frustrated with those. But let's go back to something I told you the other day that I said is going to come in handy. I plugged in 2 into my box and it didn't work. But let's go back to, I believe it was called the remainder theorem, that says if I want to do f of 2, if I want to plug 2 into that function, can I not use synthetic division to plug into it? So do you see what you actually just did? Not only did you test to see if 2 was a factor or root, but in essence, in doing that, you also plug 2 into this function. So I'm just going to make a list over here. When I plug in 2, I get negative 12. F of 2 is negative 12. The reason that's going to come in handy, what if you found out that f of 3 was 0.2 or something? I don't know, that's just random. But what if you find out that f of 3 is something really close to your y-axis, or your x-axis? Think about it. If you plugged in, you're using your synthetic division here, and you plugged in this value right here, and you got something really close to that x-axis, guess what? You're close to a root. These polynomial functions are smooth functions, meaning that you can draw them without even lifting your finger or your pencil. They're smooth functions. So if you get something really close to 0, negative 12 is not very close to 0, but if you get something that's really close to 0, then I would try another number that's really close to that number. It kind of gives you an idea of what to try. If 2 was close, I'd probably try 3. Okay. So here we go. Positive 2 didn't work. I'm just going to scribble out the positive there. We're still left with -2. Somebody pick one, so you'll probably look at it. Which one? -2. Let's try -2. So we bring down 2, we get -4. Add those two together, -7, 14. -11, 14 is 3. 3 times -2 is -6 is 0. When I plug in -2, I get 0. That is a 0 of that function. And not only did you find the 0, but you also factored it in doing so. Because now, since I know that x plus 2 is a factor, and when I divide x plus 2 into that, I get this, then I've broke it down. So what I can do, I can now rewrite f of x equals that stuff as now f of x equals x plus 2 times 2x squared minus 7x plus 3. And why would I want to do that? Because I can factor that. That's quadratic. Once you get it broke down to quadratic, you no longer have to do all this. Now, could you now take this 2x squared minus 7x plus 3 and try to break it down still by using these? Yeah. I don't know why you would want to. You have now a new way of factoring. If you want to make your list instead of factoring like you do normal quadratics, you can make your list and try synthetic division if you find something that works. I'd rather factor by hand. Since the 2 is out front, we're going to have to use bottoms up. Turns it into x squared minus 7x plus 6, which is x minus 6, x minus 1. Since we moved the 2, we divide them both by 2. So my new factored form is x plus 2 times x minus 6 over 2 will be x minus 3 times, since you can't reduce that, bring the bottom up. That's the factored form, but that's not what that actually means. It says find all of the real and imaginary zeros. To find the real and imaginary zeros, I said y equals 0, and I solved it. I have 3 of them. My 3 zeros are now, we knew one of them worked up here, -2, there's 1 0. Positive 3, there's another 0. And set this equal to 0, add 1 divided by 2, and you get 1/2. There's my third 0. Another one. Find all of the real and imaginary zeros for each polynomial function. Let's list all of our PR, our possible rational roots. All the factors of 8 over all the factors of 3. We like prime numbers. Prime numbers are good. All the factors are 8. 1, 2, 4, 8. Over 1 and 3. All the combinations of those, 1 over 1 is 1. 2 over 1 is 2. 4 over 1 is 4. And 8 over 1 is 8. 2 over 1, or excuse me, 1 over 3. And, let's see, 2 over 3, 4 over 3, and 8 over 3. No repeats there. So that's all my possible rational roots. And again, it's all the combinations of your excuse me, last term over your coefficient of your first term. So that's all the possible rational roots. Let's talk about an easier way. So we're going to go through, and this is all the possible rational roots. What is a root? What's another name for a root? A 0 or an x-intercept. That's what you're looking for. You're trying to solve this equation. You're trying to find all the real and imaginary zeros for the polynomial function. So there's all the possibilities. So what's the best way of working this? Why don't you graph it? Instead of going through and trying every one of those and seeing which one would work, why don't you just graph it? Let me type that. We need graph. and you get some polynomial function. And later on in the chapter, you're gonna talk about basic forms of these polynomial functions. And x to the third, I don't know if you've noticed it yet. X to the third, although it could be a little taller in places, a little skinnier in places, is always up, down, up. It always has that basic shape. Okay? X squared always has the same basic shape. So you can kind of tell what it's going to look like just by seeing what that is. Now let's clean this up and work on this for your graphing. Let's zoom this thing in. Let's change our window because we have lots of wasted space over here. We have lots of wasted domain. So let's only run this from like -2 to 4 maybe. So go to your window, change the window from -2 to 4. Let's see if that makes your graph look a little better. And even though, I mean, you could change your Y, but we kind of know what it does. We're only concerned with this, and this, right? Does that give you an idea about what to test? Each tick mark, notice on my window, my X scale and my Y scale, each tick mark tells me 1. So this is 1. Your first 0 is not quite 1. Your second 0 is a little bit bigger than 3. And this -0 is a little bit smaller than -1. So now, what do you want to try? Should we try 1, 2, 4, or 8? They're not going to work. Okay, we only need one that works. What do you think this is? I would say 2/3. It's less than 1. It's a little bit over the half, right? I would say 2/3 is probably pretty accurate. So we're going to test 2/3. 2/3 goes in the box. 3, -8, -8, and 8 goes next to it. We're saying is 2/3 a root here? Bring down 3 and multiply. What's 2/3 times 3? 2. -8, 2 is -6. And you'll learn this. If something works out, because you probably thought this is going to be a nightmare having to use 2/3. For some reason, if it works out, look what you always have down here. It usually ends up being multiples of 3. It seems like kind of nice. 2/3 of -6. Let me show you how to do this in your head. What is 1/3 of -6? -2. Just divide by 3. Take a third. And then 2/3, therefore, since 1/3 is -2, 2/3 would be -4. 2 of it. -8, -4 is -12. 2/3 times -12. 1/3 of -12 is -4, so 2/3 would be -8. Amazingly it worked. First time. So you just broke it into x minus 2/3. If 2/3 is the root, x minus 2/3 is the factor, and 3x squared minus 6x minus squared. That's your new g of x. Something else to point out. When you use fractions, look what you're left with. Austin, see anything in common? They all have factors of 3. This will happen every time you have fractions. Every time that you're using synthetic division with a fraction, you're going to have, well, I say every time, most of the time, you're going to have a factor, whatever that bottom was, you're going to have a factor over here in that. Take that factor and pull it out front. So we're going to pull the 3 out of that. We're going to clean this up some. Pull 3 out of 3x squared, you're left with x squared, -2x, and -4. And if you just want to clean it up, if you just want to get rid of these fractions, whatever you pull out, you could always distribute that just to get rid of that fraction. It just works out like that. Because look, if you do multiply that back out, 3 times x is 3x, and 3 times -2/3 is going to be -2. So now trying to break that down again, Josh, x squared minus 2x minus 4, will that matter? What multiplies to give you -4, make you a list there. Multiplies to give you -4, and the only options are 1 and 4, or 2 and 2. Will either one of those add give me -2? So we'll not factor. So we need some other way to find a 0. We know one of them. One of my zeros is obvious. Set this equal to 0, or just look right here either way. 2/3. That's 1. Now what if I'd have left it like this? How do you set that equal to 0? Can't. 3 will never equal 0, so what can you do? You just, if you left it here, you could have dumped that. One of your zeros is 2/3. But how do we get a 0 from this? X squared minus, it's not factorable. So any other idea? How do you find out what makes that equal 0? Always start out with your discriminant first. B squared minus 4AC, Mary. Here's what we're plugging in. That's what we're trying to find the zeros of. We couldn't factor, so we're plugging into that. What's B squared, Mary? Is it 4 plus 16? Sounds good. That's your discriminant. B squared is 4 minus 4 times 1. Yeah. So now let's plug in the rest of it. Negative B is 2, plus and minus, square root of 20. Seth, break that down for me. Good. So 2 plus and minus square root of 2 root 5 over 2a, which we can, that'd be very easy to distribute probably there. Your other two answers are 1 plus and minus root 5. And that is two answers. 1 plus root 5, 1 minus root 5, those are the other easy. Just throwing this out there, we'll learn about it later, but you might need to know it now just to make things a little bit easier. You might have already noticed. X to the third, how many zeros do I have? 3. X to the fourth, how many do you think it'll have? 4. X to the fifth, not 5. X to the sixth, not 6. Sometimes they'll repeat though, because some of you might be saying, but a parabola it's x squared, but sometimes it only has one solution. But it has one solution with a multiplicity of 2. That solution is a solution class. It'll always, if it's x to the third, it'll always have 3 factors, and we'll have 3 solutions. They're not always unique solutions, but we'll have 3. Which this leads to what I just said leads to simply this multiplicity of roots. If a factor x minus c, and we know that can be x minus 2, x minus 3, it can be x plus 4. If a factor occurs k times in the complete factorization of the polynomial, then c is called a root of multiplicity 10. That makes no sense. Let me tell you what that is. X squared minus 2x plus 1 equals 0. Factors into x minus 1 times x minus 1. I just told you this should have 2 solutions. It does. What are the 2 solutions? 1 and 1. 1 is a solution, or a root, or a x-intercept, or a 0. 1 is a solution of multiplicity 2. It's a solution clause. That's all that says. If something's a solution, if something's a factor multiple times, then it has that solution of a multiplicity. And now this next part is pretty neat. If something has an odd multiplicity, if 1 is a root 3 times, then the graph crosses the x-axis at that point. If something has an even multiplicity, think about what that graph would never look like. That's a parabola, correct? Y equals x squared minus 2x plus 1, that's a parabola. Does it cross there? Does it cross at 1? Remember what we said about it? How in the world can a parabola only have one solution? It touches. It comes down, it touches it, and then it goes back in. If something is a factor or a root an even number of times, it doesn't cross. The graph will cross, the graph will touch. Once again, if it's a factor or a root an odd number of times, it crosses like 1. If something's a root once, it'll cross that. If something's a root an even number of times, it will cross, it will touch. Look at this problem. We have 2 roots here. Garage, what are they? What makes this equal 0? what's the multiplicity of that? How many times is square root? Does everybody see that? Because this is x minus 3 to the second. That means if you listed these out, that's x minus 3 times x minus 3 times x plus 14 times x plus 14 times 5 times. So x equals a 3 has a multiplicity of what? 2. X equals negative 14 has a multiplicity of 5. So if what we said was true, and that's the reason I worked this problem, if what we said was true, when we graph this, I'm about to graph this show. When we graph this, your graph should do what at 3? Cross or touch? Touch, and should do what at negative 14? Cross. Let's try it. Here we go. X minus 3 to the second times x plus 14 to the fifth. I'm going to go to Zoom standard before I can go into that. Zoom standard, Zoom Zoom. Here's your graph. At 3. Oh, there you go. Let's go back and stop something. X minus 3 to the second, x plus 14 to the fifth. So there we go, let's graph it. Here's what the graph will look like. You're going to cross at negative 14. You're going to touch at positive 3. So you're going to have, let's see, that's positive. So it's going to come up, then it's going to come down, it's going to touch. So it'll look something like that. So graphic calculator works. Crosses at negative 14, touches at 3. Last problem. State the degree, 5, highest power. That's all you got to do there. Your degree here is 5. Find all the real and imaginary roots of each equation, starting, stating the multiplicity when it's greater than 1. First thing is shares x's. Factor out x to the third. Actually, factor out 6x to the third. You're left with x squared plus 4. Will x squared plus 4 cancel? Or, excuse me, factor? No, not unless you do factor with imaginaries. We don't have to. Since it won't factor, let's set each of these equal to 0. 6x to the third equals 0, divide by 6. X to the third is 0, so x must be 0. When you set this equal to 0, you get 0. Because if you get rid of the third, you can come over and cube root if you want to, it's still 0. So x equals 0 is a root with a multiplicity of what? 3. 6 times x times x times x equals 0. So either x is 0, or x is 0. Then we've got to set this equal to 0. X squared plus 4 equals 0. Don't forget your imaginary section. We subtract 4. Leaves me with x squared is negative 4. To get rid of a square, we do plus and minus the square root. So x equals plus and minus. Break square root of negative 4 into the square root of 4 times the square root of negative 1. Michael, what is that? 2i. Square root of 4 times the square root of negative 1. There's your 5 roots. You have 0 is a root 3 times. 2i is a root, and negative 2i is a root. Now, what would that look like? What happens here? Would it cross, or would it touch? Cross. Multiplicity odd times. Now, what happens at 2i? Where is 2i? Will it cross or touch there? Guys, if you're graphing with an x and y axis, 2i does not exist on the x and y axis. It's not going to cross or touch anywhere else. Okay, these are imaginary. They're not real. This is a real point. So it's going to cross at 0. It's going to come up here and do something weird. Up here, come down, and go back up, but it's not going to cross anymore. So your only real solutions are 0, 0, and 0.